The study of algorithms to solve problems by a computer has found some very interesting facts. These interesting facts lead to some very fundamental questions of what kinds of problems we can solve efficiently. So let me talk about this and about intractable problems and the class NP, certain kind of problems. So basically, some problems seem to take a lot of time to solve by computer, and there's no easy way to get around it. And it's not because they have a lot of work to do, like sorting a billion integers clearly is going to take a long time because there's a billion of them, but for more fundamental reasons. Finding a path in a maze, even though the maze is not so big, may take a lot of time. And for such problems, we do know of algorithms, so they are solvable, but somehow the algorithms are all inefficient. Their temporal complexity seems to be exponential. So a major example of this, which kind of crystallizes the issues and poses the most fundamental question, is the class of NP problems. So NP is a set of algorithms solving problems, and a problem is in the class NP if a very particular condition is satisfied. So if someone gives me a solution, I can easily verify, check it, that it's really a solution, and the check will be done in polynomial time complexity. So what that means is that the algorithm is non-deterministic polynomial time. Non-deterministic means that the algorithm has a kind of built-in oracle. It can pick the right solution, like it has a divine inspiration. All the algorithm has to do is verify that the solution is correct. So that's NP. But even though verifying a solution might be easy, finding the solution from scratch, calculating it, if you don't have an oracle or any divine inspiration, this seems to be much harder. This seems to have exponential complexity. So there seems to be a fundamental difference between checking that a solution is correct and finding a solution from scratch. So let me give an example. So this example is called satisfiability of digital circuits. So assume I have a digital logic circuits built with logic gates, two kinds, AND gates and NOT gates. So the AND gates have two inputs. If both of them are true, the output is true, otherwise the output is false. The NOT gate, the output is the inverse of the input. And the whole circuit is connecting AND gates and OR gates, but without memory, so there's no cycles in there. It's a pure Boolean function with n inputs and one output. The question is very simple. Is there some particular set of values for the inputs, true and false, on the different inputs that makes the output become true? Very simple question, right? This problem is in NP. Why is it in NP? Because we can very easily verify a solution. If you give me a solution, all I have to do is follow the different AND gates in the circuit and verify that the calculation is done and that the output is true. Very easy to verify. I just have to go through all the AND and NOT gates. But it's very hard to find the solution if I don't give it to you. And in fact, after several decades of work by very smart computer scientists and mathematicians, nobody has found an algorithm that does better than the real naive one, which tries all 2 to the n possible inputs. So no existing algorithm does substantially better than that. The best known algorithm still has exponential time complexity, and it's strongly suspected that no polynomial time algorithm exists, but we have no proof of it. So this has in fact led to the following state, that there are two possibilities. Either no polynomial time algorithm exists, and then you have to prove that, or a polynomial time algorithm exists, and then you have to show the algorithm. Neither has been done. If you succeed in doing this, you will surely win the Turing Award, which is the equivalent of Nobel Prize for computer scientists, and you will be eternally famous. This is the $1 million question, and in fact, there is a $1 million prize for this question. Is P equal NP? Is the class of problems that takes polynomial time the same as the class of problems that can be checked in polynomial time? Is finding a solution as easy as verifying a solution? And in a more philosophical way of saying it, can creativity be automated? This is in fact a very deep question. It is the most fundamental unanswered question in computer science, and in fact it goes much beyond computer science. Since computers are physical artifacts running on physical hardware that must obey the laws of nature, a number of people think that this is actually a new physical law. Just like the laws of thermodynamics were postulated because people could not build perpetual motion machines, well, maybe P equal NP not equal NP should be postulated as a property of the universe, a physical law. So this is really a deep question. So we can actually say a little bit more about this situation. Some of the problems in NP are special. They're not all the same. Some of the problems are very special because if you solve an algorithm, if you have an efficient algorithm for one of these special problems, then you can solve all problems in NP efficiently. So these problems are called NP complete. So that means if you find a polynomial time algorithm for any NP complete problem, that means all problems in NP have polynomial algorithms, and in fact, at that point, we will know that P is equal to NP. So all you really have to do is focus on the NP complete problems. They are, in some sense, the hardest problems in P. They're really the core. And the problem I just told you about, satisfiability, is in fact an NP complete problem. So in this diagram, we kind of see the situation today. So this one assumes P is different from NP. That's what most people believe. That in that case, in the class NP, we have P, which are the polynomial time problems, which are in some sense easy, and we have NP complete, which are in some sense the hardest problems in NP. Now, if P were to be equal to NP, then these three sets, NP complete, P, and NP, would all be the same set, of course. We don't know if it's like that. So you might say, this is all very interesting, but it doesn't really affect me. You know, practical computer science, hard-nosed designer of cloud computing systems. I don't care. Well, in fact, you should, because NP-complete problems are extremely common in practice. In fact, they are a dime a dozen. They're all over the place. So if it's like that, how can we live? How can we survive in computing if we're surrounded by all these very hard exponential time problems? Well, there are practical tricks. Sometimes we can be a little bit less demanding. For example, we can give an algorithm that gives an approximate answer, or an algorithm that sometimes throws up its hands and says, I don't know. And if that happens, tough luck. Another NP-complete problem is the traveling salesman problem. This is a very famous one. So we have a person, a traveling salesman, let's say, who has to visit N cities in some kind of in a country, and has a route between the N cities, and wants to have the total visit time, the total distance, sorry, between all these cities be minimal. This is an NP-complete problem. It's very strange, because it's in some sense equivalent to satisfiability, even though on the surface it looks very different. Now, if we're happy with an approximation that's up to 10% accuracy, then we can find a polynomial time algorithm. So it's possible to live with NP-complete problems, but it's not always very nice because we have to cut a lot of corners. So the open question is still there. Is P equal NP?